Standard molar enthalpies of formation. Elements themselves have an enthalpy value arbitrarily set at 0. Any reaction of an element with a different element or elements will change the enthalpy of the system accordingly. Your data book has a list of enthalpy values that correspond to the changes in enthalpy by the formation of 1 mole of the specified molecule or compound from its elements at SATP. Your data book will not include the subscripted M. Under standard conditions, some elements can exist in more than one form. Carbon, for instance, is either graphite or diamond under standard conditions. Graphite is generally considered to be the standard state of carbon and therefore has an enthalpy of formation of 0 kilojoules. Diamond is positive 1.9 kilojoules per mole. A variation of Hess's law allows you to calculate the enthalpy change for almost any reaction between compounds by using the compound's enthalpy of formation. This potential energy diagram represents the 2 steps of photosynthesis. The first step sees the decomposition of reactants into their elements. The second step sees the formation of products from those elements. Looking at the second step first, the amount of energy released from the change in enthalpy of the formation of carbon dioxide and water is shown as sigma, which means the sum of, delta H formation, that is, the sum of all the enthalpy changes as elements form compounds. The first step is actually the sum of all the enthalpy changes as compounds decompose into elements. And since the energy involved in decomposition is the negative of the enthalpy involved in formation, we can show it as negative sigma delta H formation. We're actually interested in the net energy involved, which is the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. Let's have a sample problem. What is the standard molar enthalpy of reaction for the combustion of methane? Now there are 2 ways to do this. You can either use Hess's law as we have in the past, where we have the formation reactions of each component in the combustion reaction equation with the corresponding enthalpies and manipulate as appropriate. Or the way we're going to do it. Add up the enthalpies of formation of the reactants and subtract that from the total enthalpies of formation of the products. Either way, you'll get the same answer. Start by writing out the required properly balanced target equation. I want to restate the formula we're going to use. Remember that to calculate the enthalpy change of a substance, we multiply the number of moles of that substance by its molar enthalpy. Next in your data book, we look up the molar enthalpies of formation. You'll not find the molar enthalpy of formation of oxygen in your data book because it's an element, and all elements are assumed to have a standard enthalpy of formation of 0 kilojoules. So the combustion of methane, as written in the balanced equation, releases 802.5 kilojoules of energy. Since the equation is written as showing 1 mole of methane, then the molar enthalpy of reaction is negative 802.5 kilojoules per mole. Thermal stability. The ability of a substance to resist decomposition is called thermal stability. You might have noticed in your data book that nearly all the formation reactions are exothermic, that is, the system releases energy as the product is formed. A decomposition reaction is the opposite to a formation reaction, and so is the change in enthalpy. If 206 kilojoules of energy is released by the formation of zinc sulfide, then 206 kilojoules is required to decompose it back to its elements. The greater the amount of energy required to decompose a compound, the more thermally stable it is.